through sort of this intro stuff, and then we've got all of the measurement aspects, and then we finish up talking about chemical reactions, and then they just have to throw the balancing equations in at the end. So there's sort of parts to this, and we're going to go roughly through the order that they have. But just first, some basic definitions. So chemistry, all of your sciences are considered the study of, so they're sort of an ordered and logical process. So this is the study of what? Chemicals. And so chemicals are all made up of elements, atoms. Those all fall into the category of matter. So it's the study of matter and the changes that it undergoes. So you don't just find elements, you find compounds. You don't just find just pure compounds, you find things that are mixed together too. So there's lots of different combinations, the study of matter and the changes it undergoes. So this is one of the reasons why I say, like, having the PowerPoint sometimes helps, because you can just add stuff in as we go rather than trying to write it on some other separate paper and then put them all together at the end. So matter. I always think of matter as a noun, okay? So it's kind of like a person, place, or thing. So matter is something that has two characteristics. It's anything that has has mass and takes up space. See, you may not have even remembered that from chemistry, like in high school. Like sometimes those things just come out of your mouth and you didn't even know that you remembered it. So it is anything that has mass and takes up space. So when we talk about mass, we talk about weight. Okay, so heaviness of something or lightness when talking about mass. But I said it's a noun. You can find matter as a solid, as a liquid, as a gas. So it can exist in these three states. So if you have the same substance of matter, which of these states will those pieces or particles be closest together? Solids. So solids, in fact, are so close together they touch. They get packed together very tightly and form a very regular, rigid arrangement so that there's no real air space between them. So they're solid. Okay, so they have resistance if you press upon them. So they say in this that solids have a definite shape. Some of them you can bend or you can roll, but if it's just sitting there, it won't change its shape. And it also has a definite volume. So what happens to a solid when it melts? What happens to those particles? Do they stay that way? Yeah, they actually spread out more. Okay, so instead of being all like packed in super tight as that solid, now these particles have some space around them, and that allows those particles to flow. They can move. So they're not stuck in that rigid arrangement. So if you push on a liquid, your hand goes into it, the particles move away, so you can disturb that. So you would say that this has an indefinite shape. So the water in the bottle takes the shape of the container, right? But if I have, and this one is 500 mils, so it's a half a liter. So if I have this, it's this volume. What happens if I take and pour it out on the floor? Is it still going to be the same volume?
Well,
same volume, but what happens to the shape? Then it's going to spread out. So in this, you have an indefinite shape, but the volume is going to stay the same. So with liquids, they're still going to keep their same volume, but because those particles can flow around each other, they're going to have the ability to change their shape. I always think of them as like they take up more room than what you would see with a solid. But what about gases, like the air in the room? So oftentimes going like this, you're really not even touching them. Okay, so they're super far spaced. Liquids like to roll around each other. Solids are in real tight. Gases, the particles rarely even contact each other. They just sort of float along and bounce off of the walls of the container. So they're going to have the largest of the volumes. And their volume is, again, the amount of air in this room is dependent on the size of the room. So they're very much dependent on what the container is. They have an indefinite shape. And you can take a gas and you can compress it. So if you've had to handle any bottled oxygen for patients, taking tanks along with, they've taken oxygen and actually pushed it into a small space, taking these molecules and forcing them into a smaller container so that it's more portable, so you won't run out so quickly. So it has an indefinite volume. You can compress gases, forcing them into smaller spaces. You can't do that with liquids and solids. You can't take that water and force it into a smaller volume. It has that definite volume, but gases don't have that. So we'll actually, later on in upper chapters, we'll talk about gases and how you can compress them and how pressure and volume and temperature changes affect them. So then the last question. So in terms of energy, which do you think has the most energy, a solid, a liquid, or a gas? And think of energy as being like the movement of the molecules. Which molecules are moving the fastest? Gases. So these have the highest energy. Which one has the lowest? Solids. You've got to cool them down so that they stop vibrating so fast so they can pack in tightly together. So they will have the lowest energy. So when you think about matter, sometimes the same substance will look different, like ice, water, and steam. It's all water. They may look different, but they're made of the same particles. So what's not matter? Something that we mentioned on the previous slide. Something that doesn't have mass or takes up space. It's energy. Well, that's an example of one. So you can have thermal. So I don't know if you can really feel it it's kind of hot in here today. Usually you put your hand on the desktop and it's cooler. So that's actually transferring heat from your warm hand to the cooler. It almost feels like it might be about the same. We're not getting a lot of heat transfer. I don't know what they've done to the heat exchanger. I think they think it's January, so clearly it should be cold. So clearly we should have the heat on in here. It's not. And so somebody didn't get the memo. So they turned on they didn't turn on the AC. I think they didn't necessarily turn on the heat, but they haven't run the AC to move all this air around.
North Carolina heat coefficient is what
Yes, that's exactly right. But energy, while matter has mass and takes up space, energy is defined as the ability to do work. So it's the ability to do work. So if you think of matter as a noun, this is a verb. This is an action. Okay, so it's doing something. So thermal energy is heat transfer from a hot thing to a cooler thing, right? So if you hold like a piece of ice in your hand, the heat from your hand is transferred to that ice. What's another one? What's in here? What's another example of energy? Okay, you have in the body, so like what would you think of? Okay, electrical. So that could be like nerve impulses. Okay, that could be the electricity, the lights in here. Electrical is flow of particles along a wire. What else? Thermal, electrical. If you ate dinner, what's going on now?
Oh, you mean if
digestion, and that is chemical energy. Okay? Chemical energy. Oh, that's another one. So chemical energy is the energy that's contained within chemical bonds. So in digestion, you're taking really big proteins and breaking them down. You got to break them down, break them down, break them down. So they're so small you can absorb them. So this is the energy in chemical bonds. Sorry, that says wire.
saying like
But peristalsis, that's what?
that's supposed to do with attraction.
So that's movement.
Oh,
Okay? So that is,
more energy left.
that's another, so there's all these different examples of energy. Mechanical. Mechanical is movement. So walking, writing, chewing, swallowing, the movement of food along your GI tract, peristalsis, that's all mechanical. So these are just some of them. Ultimately, all the energy comes from where?
Light.
Yeah, from the
Sun.
sun. So solar. In fact, we're starting to make use of this a little bit more. I've seen more and more of the solar farms, especially if you're driving along 95 every once in a while, you look over and you see these big acres, multiple acres of all these solar panels. So it's a way that towns are trying to trap solar energy. And so you don't just keep the solar energy, you convert solar energy to what?
Electricity.
Electrical
And then
energy.
window panes.
Okay, so we don't keep them. So solar is trapping the energy contained within sunlight. We don't keep the energy in one form. We can change forms. So we can take solar energy and transfer or convert it to electrical energy. We can take chemical energy from eating and use that energy in order to create movement. So energy is not like stuck in one form. It can change forms. And just some of our examples that we were mentioning along the way. So you can convert energy from one form to another. If energy is doing work, then it's which of these? Kinetic or potential? Kinetic. Okay, so think of that as active energy. So that's the lights being on. That's the food getting digested. Okay, that's moving along. All of those, this is active energy. But if you are laying on the couch, you're not doing mechanical energy, but you have the chemical energy there to produce that movement. But it's not doing anything right now. That's really what potential energy is. So they think of potential energy as stored or inactive at the moment.
Or would it be like passive energy?
Passive, or you could think of it as just being like, just not being needed. If I flip the lights off, there's still potential energy in the wires, but we have to complete the circuit. As soon as you complete the circuit, it's going to be able to flow and the filaments will glow. Same thing, if you've got a candy bar to eat on the way home, a granola bar to eat on the way home, there's your potential energy. So it's not been eaten, but it has those chemical bonds. So there's energy contained within the bonds. The only way to get the energy out is you would have to eat it. Okay, and then digestion would help with that process. So that's the stored, inactive, uneaten candy bar. Like they always think of the rock on the ledge, like if you've ever watched Roadrunner and Tweety. If you've ever watched that, where he's always like right on the very edge. So it could fall, and if it falls, that becomes active. But it's sitting up there at that time, so that's considered potential. So we're going to talk more about energy, and they call that thermodynamics. So we'll talk a little bit about that and how it's involved in chemical reactions in the semester. But if we take matter, solids, liquids, and gases, and we look at what they're made of, we can broadly divide matter into two categories. They're either mixtures or they're pure substances. So most of the things that you come in contact with are mixtures. So mixtures are when you have things that are physically combined. And they can be combined in any ratio. So think of coffee. Some people's coffee and another person's coffee, like there's some that, so my dad like grew up in like black coffee. It was like, this is like, when you become an adult, this is what you drink. My mother did not feel that way. She was like half cream, half coffee. Like, so she had a Blanco coffee, like very white. So variation, so that's physically combined, and it's an indefinite ratio. You could use a lot of coffee or just a little bit. You could have a lot of cream or just a none. So there's a varying ratio that can exist. It may not be simple to do, but mixtures can be separated. since they've been physically mixed together, you can physically separate them. So for the black coffee, so in making the coffee, you had to run hot water through those coffee grounds and it dissolved all the soluble components that was in the coffee beans. So now you've got some caffeine in there, you've got some of the tannins, you've got some of the colorings, and you've got a lot of water. That's the biggest part of that mixture. If you boil away the water, you would be left with the freeze-dried coffee stuff, right? So like the instant, have you ever had instant coffee? But the instant coffee, that is in theory, they've taken the coffee and taken all the water out. So they have separated the water out of the rest of the components. And so that's a physical separation. So to physically separate, you could boil. You could freeze the substance. So some of the substances would freeze, the other would stay liquid. You could separate them that way. You could filter them. Okay, if you had a small enough filter, you could separate small and large particles. Pure substances, on the other hand, you can't do that. Pure substances are made of a single unit, whether it's made of one element or two or 5 or 10, they are combined in a fixed ratio. They're chemically combined. They can't be separated physically. And that makes them different than the mixture. Okay, so in our big division, we have the pure substances are the green, the pure substances are the ones on the left, the mixtures on the ones on the right. So we said that these pure substances can't be separated physically, but you could identify what the individual units are made of. So the individual units can either be an element, and if they're an element, it means that all of the particles that makes up the pieces are exactly the same. And you can define the elements, and they have been discovered. We're now up to 118. They still, this is a super old periodic table. But we actually have them named all the way through 118 now. That was 2016 is when the last 4 were actually officially named. One of them is Moscovium, after Moscow. Yeah, Moscovium is 117. So those are ones that aren't even on there. And I always give you this. Okay, you will always have this. You never have to memorize a periodic table. You just know how to use it. Okay, and that's what we're going to talk about. And I like this one because it's got things like the zigzag line. It's got the group numbers that tell you stuff about electrons. So this really, I will always give you this. That's why it's laminated. Please don't take them home. Please make sure you just put them back on the stack on your way out every night. That would really help. But I'll always give you this. And it's just because sometimes, for you, turn around cranking your neck, it may be hard to constantly look at it. And so that way, everybody has the exact same one. So an element is defined as being the smallest particles are identical. So they give you an example of copper. So copper is element number 29. So they identify it by the number at the very top, and its symbol is Cu. But then this one, they show you this copper like copper wire. So it's nothing but the exact same pieces, and if I split this into smaller and smaller pieces, it would still be exactly the same. There's no way that I can physically or chemically separate this into anything that's different. So very uniform. These small pieces are all called atoms. So elements are all made of the same atom type. And the periodic table gives you the list of them. You don't have to memorize every single one, but I will give you a list of ones that you need to know. Okay, so we know about 30. There's 118. But the 30 that we're going to talk about are ones that we talk about all semester. So it really helps if you know names and symbols with those. Compounds, on the other hand, They may look uniform. When you look at a compound, you may not be able to see any kind of differences. However, the smallest particles are made of 2 or more elements in a fixed ratio. So in a compound, it's 2 or more elements in a fixed ratio. And so in this, when understanding a compound, you are commonly given a formula. So they give you a formula like H2O, NaCl, C6H12O6. But they're going to actually tell you like numbers of atoms in a formula, and that's always the key, sort of the trigger for it, that you know that it's a compound. Mixtures, on the other hand, I said they're physically combined. So they're just sort of stirred together, like the coffee. So an example they give is brass. And so you may not know that about brass, but brass is made by mixing copper and zinc. So you heat copper and zinc till they liquefy, and you mix them together. And what the zinc does is it makes the copper harder, okay? Because copper you can bend like a wire, but brass you can't. So brass, you make it into candlesticks and you make it into other things, like we used to have the little funny fireplace things in front of that we weren't allowed to touch, and they would get all tarnishy looking. But that's the reason that they add the zinc, is because it adds hardness. So it helps to keep its shape so it's not quite so bendable. But those are physically combined. They were heated, so they melted, stirred them up. When they cool, it leaves you with that shiny brass color. Okay? So does this look the same? Like if you look at like a piece of brass, does it look uniform, like on one end or the other end? Like they give you it looks like is it a tuba? It's kind of a funny looking trumpet. That's what I was thinking. It could be a trumpet because it's got the 3. We'll just say. So for a musical instrument. But when you look at it, like if you look at any part of like any of those tubas or saxophones, if you look at those, the brass instruments, like any part of it, whether it's up at the top or up near the bottom, it has that same shiny appearance, okay? So it looks the same. They call this homogeneous. And the word homogeneous is just a Latin term, means the same. So homo means the same. So it's going to look the same throughout. So you couldn't take a piece of brass and break it and be able to look at 2 different parts. Even though they're physically combined, they have a uniform appearance. So a uniform appearance, they don't separate out. So the coffee example is a homogeneous mixture, okay? So the coffee, like if you pour coffee into a clear glass and you look, it's just going to look like a dark brown liquid. If you add the cream and you stir it up, then it's just going to look like a creamy liquid. But it's homogeneous. Those things are physically combined, mixed together in the cup, and they look uniform. But their other example is if you take some pennies and throw them in water. Do the pennies disappear? Do they mix and stay mixed? No, they separate out. Okay, so where you have a solid and a liquid combined, the solid settles or it would float depending on its density. But in this one, if you put a penny in water, it doesn't dissolve. You can still see there's 2 things. You can tell there's water and you can tell that there's a penny. That's heterogeneous. And the word hetero means different. Homo means the same. Hetero means different. And you can see layers. You might be able to see pieces. You might be able to separate it physically just by pulling them apart. Like you could fish the penny out and separate these 2 components in the mixture. With the coffee, it's homogeneous and you can't see anything. You'd have to go through to be able to separate it. So I gave you some examples and we'll do a couple more. But in the first one, just tell me, is it a pure substance or a mixture? Is it something that's found as a uniform defined particles, or is it just 2 things physically combined? Gatorade. It's a mixture, okay? So this is a mixture. Now, if it's a mixture, the next question is it uniform or can you see layers? Okay, so that makes it Homogeneous. Okay, so if it's a mixture, you can identify it as being homogeneous or heterogeneous. Chocolate ice cream. It's a mixture because what's in it? Cream, sugar, cocoa. That would be like the simplest chocolate ice cream you could make. Okay, they add a lot of other weird things to it now, but that would be like the simplest of things. So that's definitely a mixture. Can you see parts to it? Like if you get a scoop, does it look the same at the top and the bottom? Yeah, homogeneous. But what if you had chocolate chip ice cream?
That would be different.
So that would
It'd
be
a mixture, but it would be
right. So it's still going to have cream, vanilla, sugar, but it's got chocolate chips in it. And those chocolate chips don't just mix uniformly. They're going to leave speckles. Even if you put it in the blender, they're still going to leave little funny little bits in there. So it's still a mixture because we have physically combined them, but it's got pieces you can see. That's heterogeneous. Distilled water. So here's how you make distilled water. You take water and you boil it to create steam. You collect the steam and you allow it to condense back into the liquid form. So what is that? Is that a pure substance or a mixture? It's a pure substance. Is it an element or a compound? It's a compound because it has what? HNO. It has hydrogen and oxygen. So in those, you can look and compare to what's on the periodic table as a means of determining, okay, is that a pure substance? Is it an element or a compound? So this one is a compound. Now what about tap water? Okay, so it is a mixture. Tap water is going to have some small ions dissolved. Hopefully it doesn't have too much. Sometimes it gives it a little off flavor. like in theory, water shouldn't taste like anything. But when your water, like in August in Wilson, the water in Wilson in August, you're like, this smells funny. Like it just like starts having that swampy smell to it. Tap water, it's got chlorine. They chlorinate water. It's a way of being able to make sure it's purified. So it's got water. It may have very small amounts of salts. If you have old pipes, it may have very small amounts of metals in it too, like copper, trace amounts. So, but that would make it a mixture or pure substance. It's a mixture. And in theory, when you pour it in your glass, should you be able to see anything? No. Okay, so it should look homogeneous. Okay, but it's not the same as distilled. Distilled is nothing but H2O because when you boil, all of that other stuff gets left behind. So any ions, any metals, anything else in that water is not going to become steam. Only water molecules will condense and be collected. So in lab, there'll be times that I'll tell you, like, make sure you use distilled water. And that's really why. It's because we don't want any of the other stuff that's there. Okay, so we'll do a couple of these and I'll leave the rest of them and we'll come back to those ones later. So what about sodium chloride? Sodium chloride is commonly called salt, table salt. So it's a pure substance. It is NaCl. Okay, now if it's iodized, then it's a mixture because they've added small amounts of iodine to it. But if it's just NaCl, if you go and you see just a formula, then you assume that there's nothing else in there except what that formula says. But it is a two substances chemically combined. So you'll find 1 sodium per 1 chlorine, 10 karat gold. So gold, when you see gold, you're like, oh, but gold's over there. That's AU is its symbol. But 10 karat, what does that mean? Yeah. So the carat in gold is actually telling you how much other metals are in there. 24 karat gold is pure gold. And you can take 24 karat gold and bend it. So do you want to wear 24 karat gold earrings? They would like fall off. You'd be out a whole lot of money. Okay. So instead they actually heat gold. And they add other elements to it. They can add iron to it. They can add copper. They can add zinc to it. They add small amounts because it increases hardness. Okay, so you have 14 karat gold and 10 karat gold are two common types of gold that are used in making jewelry because they're nice and hard. They're not going to bend and they're not going to wear away too fast. So if you see 10 karat gold, you would really need more of an explanation of what 10 karat means. Okay, so you know then this is, from my explanation, it is a mixture. But if you look at gold, does it look the same throughout? Yeah, so it is homogeneous. Salt water. It is a mixture. It's a mixture of salt and water. So if you took pure water, put a teaspoon of table salt, stir it up, does it dissolve? Yeah, so it is also oxygen gas. It's a pure substance. O, it's element number 8. So it's a pure substance and it is a element. Even though it exists as what? Does it exist as O? It always, when you talk about oxygen, you've got to give the patient what? O2. Okay, so that means O2, the formula tells you how many atoms of each. But when you look at that formula, it's nothing but O. Even though there's 2, it's still considered an element because those 2 atoms are the same thing, okay? Compared to CO2. So if you had to give somebody, or if you were trying to measure amounts of CO2, CO2 would be it's a compound because it's got carbon and oxygen, okay? But they're chemically combined in a fixed ratio. So you can look at those ones. We will cover those ones. I wanted to cover a little more about the periodic table itself. So like I said, the periodic table is this organization of the elements. There's a total of 118. They're listed according to that number at the top. We'll talk about that as the atomic number. We'll talk about that in chapter 2. So you notice that in the periodic table you have and the one on the wall, they're just listed according to these symbols. So they're either 1-letter symbols, which are always capitalized, or they're 2-letter symbols where the first letter is capitalized, the second letter is always lowercase. And that's a way that you can actually tell how many elements would be in a compound based on that formula. So if you see something like Cr2O4, so capital C, little r, that tells you that that's one element. And then O by itself tells you that that's one element. So you look for the capital letters. So you would know that there's 2 elements in that formula. It's chromium. I think it's dichromate. The rows across, they call the periods. That's going across the horizontal. And going down, they call them the groups. So periods go across, and if you follow across, you see that they increase it by that number. So like H is hydrogens over on the very upper left corner, and if you go straight across over to HE, that's helium. Then going down to the next row, you have Li, which is 3, then Be, which is 4, and they keep going and increasing by that number at the top. So they sort of just increase as you go along those rows. Now the groups, they actually found that some elements had similar properties, and it really is what led to the development of the periodic table. So everything in that first column, they behave a lot alike. So H, Li, Na, K, Rb, Cs, and Fr, those, they have very similar properties. So they act the same. They call the first one, so this first group 1, and on yours it says group 1A. Those are called the alkali metals. And they behave similarly, especially in chemical reactions. So like sodium, which is Na, and potassium, which is K, they behave very similarly in a chemical reaction. Group 2A, they found that that column also had similar characteristics. They called those the alkali earth. So magnesium and calcium, that behave very similarly. So think things in columns have similar properties. The only other there's two other groups, but we'll do the ones on the far side. So group 7A, so the next to the last column, these are called the halogens. And here's a good example of how they have similar properties. So chlorine, what is chlorine? What do you use it for? Cities use it to do what? Treat water. Okay. So iodine, where have you seen iodine?
Surgical procedures.
Okay. What do they use? When do they use iodine in surgery? To clean. It's a scrub. Okay, so if you've ever ended up with the orange skin, so you had surgery and you're all kind of orangey looking afterwards, that's because you had an iodine scrub. So iodine is a topical surgical disinfectant. Chlorine is a water disinfectant. Bromine, we stayed at a place that had like a hot tub, and we used to have bromine tablets that we would like stick in the water because it would sanitize the water in between uses. So all of the ones, fluorine, chlorine, bromine, and iodine, they all have a disinfectant characteristic. And so that's some of the things that they found, that similar elements in the columns had similar characteristics. And it really helped them to figure out how to put this in an order. Rather than just having a really long list of 118 elements, they put it in this chart. And so it's done this way because things in the same columns have similar properties. The last one, group 8, VIIA. They are some of the last ones to be found of the common ones. HE is helium, NE is neon, AR is argon. What is their claim to fame? They're the what? They're all gases. They're the noble gases. So the noble gases were named this because they didn't react with things. So they like to hang out all by themselves. They don't form helium chloride. Okay? So argon exists as just atoms of argon. It doesn't make a compound. So extremely stable and can be found as pure elements. And that's sort of like the basis. We'll talk about them again when we talk about covalent bonding, ionic bonding, and why molecules form compounds. So those are just some of them, but those columns have similar properties. The other thing you can tell on this one, not on that one. Well, one interesting thing about this one, everything in black are solids, liquids, or gases. All the black. Sodium, potassium, iron, copper, nickel, zinc. They are all what? When they're a pure substance, they're all solids. So notice all the blacks. There's way more solid elements out there than liquids and gases. The red ones, those are the gases. Okay, and notice they're pretty much the ones that are all on that upper right corner, that upper right, far right side. The red ones are the gases, except for hydrogen. Hydrogen's a little oddball. Doesn't really belong where it is, but they put it over there anyways. And then there's only two that are blue. So those are what? Liquids. What's one of them? Bromine. So Br, bromine is a liquid at room temperature. And what's that? You've seen it when you've taken blood pressures. Mercury. It's millimeters of mercury. So Hg is mercury. Those are the only two, next trivia game you have, those are the only two elements that are actually liquids at room temperature. By and large, they're all solids, okay, because they all come out of the ground. They're all earthy stuff, okay, but there are gases, most of them in that upper right corner. And this always stays on there too. So just as an interesting thing. Last one. Everything to the left of that darkened line on your handout, those are, on this side to the left, metals. Metals are to the left of that little staircase line. They call it, very technical name, it is the zigzag line. Okay, so you can see where it is. They don't have it on that one. It's one of the reasons that I like this periodic table, because it is a good way to be able to tell metals and non-metals. Okay, everything to the left is metals. Everything to the right is non-metals. Way more metals than non-metals. And they as a group also have some characteristic differences too. Where are you? So metals. So if you look at a metal, what does it usually look like? Solid, liquid, or gas? Metals tend to be solid. Solid at room temperature. But most of those non-metals, they're kind of a mix, but you have a lot more what? Solids, liquids, or gases? All over here. Yeah, see where all the gases are. So all the gases, so nitrogen, oxygen, fluorine, all of those noble gases and chlorine, those are all gases. So you have a lot more gases at room temperature. Not all of them, but more of them. Metal characteristics, being that solid, metals can be pulled, like pounded into sheets. They can be pulled into wires. So they can be shaped. Pulled into a wire, and they can conduct electricity. Metal properties, all of those on this side. Some are better than others, but non-metals really have the exact opposite. Of the ones that are solid, so like looking at carbon and phosphorus and sulfur, the ones that are non-metals and solid, they're not very good at shaping. They're really brittle. So if you take carbon and you try to shape it, it'll just shatter. So they're much more brittle, not shapeable, not bendable. And these are much better insulators. Rather than being conductors, they can be used and placed around wires because they will inhibit the flow of electricity. It was understanding about silicon and the silicon chip. So they basically took like large scale wiring and scaled it down to microscopic size. And that's what's in your computers now, because silicon's a non-metal and it's an insulator. So you can take microscopically thin wires and run a circuit board to do really fast processing. And the silicon is what those wires sit in, because the silicons don't conduct electricity. And so they got figured out using metals and non-metals together to create this circuitry. When I was in school, like a computer took up like a whole wall of a room. It was like huge because everything was actual physical wires that were plugged in. So processes had to go through all this wiring. And then with the advent of the semiconductors, with using silicon as an insulator to develop these really small processing chips, we've now, basically your phone is a computer, okay? So you've got something that's now this big. People that have pacemakers, so a pacemaker is something that actually monitors heart rate, monitors the rhythm of the heart. That's a computer. So it's actually monitoring and looking at what that person's heart rate, how the electricity is flowing through the heart. And so it's this big. It's like the size of a saltine cracker, and it's a computer.
Capacitors.
Mm-hmm.
Have you seen some of the stuff they're doing with capacitors?
Yeah, just things that have used to be
power, yeah.
huge. So there are some of the bismuth and tellurium. There are some that are non-metals but down low, like large non-metals that have amazing abilities in the insulation versus the conductor properties that they have. So this is a non-conductor. So we will talk more about metals and non-metals, Lord, when we get into chapter 3, we'll talk about them ad nauseum. So you'll hear quite a bit about them. I will quit there, but I want to give you this first list. So here's your first list. Things to start looking at. Elements 1 through 20. And like I said, I've got them here. So if you look on the periodic table, just numbers 1 through 20, you want to start to learn the name and the symbol. So if I give you the symbol, you should be able to give me the name. If I give you the name, you should be able to give me the symbol for 1 through 20. The other ones that I have, and I have 10 more listed, are the ones that are here. So I have chromium, which is CR number 24. Iron going along, which is 26. Cobalt, CO. Copper is Cu. Zinc is Zn. All the way over, bromine is Br. Silver is Ag. Gold is Au. Mercury is Hg. Okay, so those ones added into the list, and the last one is iodine. We will talk about these other ones other than the first 20. Some of them just follow the normal, like carbon is C, okay, like lithium is Li. So some of them are pretty straightforward. It's just the first 2 letters, but they started running out of letters. And so that's why, like, you have sulfur and you also have sodium. And so some of them have what are termed Latin terms for them. So like the salt in Latin is natrium. So that's where Na comes from. So that's how that symbol came. So my suggestion is just make a list. Make a list, like cover them. Okay, some people do flashcards, put the name of the element on one side, symbol on the back, and then just flip through. Just do these 30, 1 through 20. Any others that I give you through the semester, I'll tell you the name of the element. Okay, so like with uranium, if I tell you that one, and when we talk about radioactivity, I'll tell you it's uranium. I don't expect you to actually know the name for it. But if you learn these 1 through 20, and then these additional 10, these are going to be the ones that we're really going to talk about more throughout the semester. So being familiar with the name and the symbol is important. Okay, so I'm going to stop there. Like I said, I will have this posted. So if you want to go back and look at any of the marked up, any of the notations that I added, you can look at them that way. You can also, the lecture will be posted online if you wanted to listen to it. Okay, so I'll see you Wednesday. Wednesday nights, if you're in my night class, we are going to have labs. So we're going to do lab 1. It's the safety lab. So if you haven't gotten your lab manual, try and get it before Wednesday, because we're going to go ahead and roll with that too.